Today, we're heading to the absolute front lines of climate change. We're going to see how the island nation of Vanuatu is using some pretty incredible science to, well, stare directly into its own future and prepare for the rising seas.
You know, for the people of Vanuatu, everything revolves around the ocean. It's their source of food, it's their highway, it's their culture. But that very same ocean, the thing that gives them life, is now becoming one of their greatest threats, all thanks to a rapidly changing climate.
So that brings us to the big question, right? How on earth do you protect an entire nation that's a sprawling archipelago of over 80 different islands, each one with its own unique coastline, all facing this really uncertain future of rising seas and more powerful storms? Where do you even start? To answer that, we first have to get our heads around the sheer scale of the challenge Vanuatu is up against. Here's the situation. Vanuatu is consistently ranked as one of the world's most vulnerable nations when it comes to climate change. A huge chunk of its population, its most important infrastructure, and basically its entire economy is packed into these low-lying coastal areas. And here's the kicker. Sea levels in this part of the Western Pacific are actually rising faster than the global average. They are truly at the sharp end of this crisis. And this is what that future could look like. If global emissions stay high, the business-as-usual scenario, the median sea level around Vanuatu could jump by almost a full meter by the year 2090. That's a change that would literally reshape the entire nation. But here's the thing. To fight back against a threat like that, you need good information. And for a long, long time, Vanuatu was basically flying blind. They were dealing with a massive data blind spot. You see, coastal flooding, it isn't just about that slow, steady creep of the ocean. The real danger, the thing that causes the worst damage, is what scientists call extreme sea level. It's like a perfect storm. Literally, it's when you get a high tide, a storm surge from a cyclone, and massive waves all stacking on top of each other. That combination is what causes catastrophic flooding. And this was the fundamental problem. The main tool for measuring sea level is something called a tide gauge. And for safety, they're usually put in calm, sheltered harbors. So as this quote from the report points out, that means it can completely miss what's actually happening out on the coast. You could have devastating floods on one side of an island, while the official gauge, just a few miles away, shows nothing all that unusual. And this slide just shows that perfectly. This is from Tropical Cyclone Pam. The graph on the left is from the official tide gauge in Port Vila. It looks like a pretty minor event, right? But the data on the right shows the enormous offshore waves that were actually hammering the coast. That difference, that's the data blind spot. So what's the result of this disconnect? Well, it's just massive, crippling uncertainty. Planners couldn't answer the single most important question. What's our real risk from a rare but totally devastating event, like a 1-in-100-year flood? And without that answer, trying to build resilient infrastructure is just a total guessing game. So a project called VanKIRAP decided to tackle this problem head-on. They set out to fill that data gap by doing something truly ambitious, something kind of sci-fi, really. They decided to build a digital ocean. The solution was to create this incredible, state-of-the-art national ocean hazard modeling system. Now, the easiest way to think about it, and it's a great way to think about it, is as a digital twin. A perfectly simulated virtual copy of Vanuatu's entire coastline, where scientists could unleash thousands of virtual storms and see exactly what happens without anyone getting hurt. So how in the world do you build a digital ocean? Well, it kind of breaks down into 3 huge steps. First, you have to map the seafloor with incredibly high-resolution satellite and LiDAR data. Second, you build a computational grid, or mesh, over that entire map. And third, you have to tell the model what the seabed is actually made of. Is it a coral reef, sand, rock? Because that dramatically changes how water moves and how waves break. And this right here, this is the secret sauce. You see how the grid is made of all these triangles? They're massive out in the deep ocean, where you don't need much detail. But look how they get incredibly small and dense right up against the coast. This flexible mesh lets the computer focus all its processing power on simulating the complex physics exactly where it matters most, right where the waves hit the shore. It's brilliant. Okay, so once you've built this amazing digital twin, it gives scientists 2 really powerful ways of seeing the ocean. One that looks back into the past, and one that looks far, far into the future. The model runs in 2 totally different modes. The first one is called hindcast mode. It basically simulates the last 41 years to see if the model's results match up with what actually happened in the real world. That's how you prove your model's accurate. But the real game changer is the probabilistic mode. This is where they simulate 10,000 years worth of computer-generated synthetic cyclones to finally understand the true odds of one of those rare, catastrophic storms.
And this is the payoff. This slide says it all. On the left, that huge shaded area is the uncertainty you get from only 41 years of historical data. For a rare event, the possible outcomes are just all over the place. But look at the right. That's the result from the 10,000-year simulation. That band of uncertainty shrinks dramatically, and the true risk becomes crystal clear. It's a massive leap in confidence.
So, you've got this incredible newfound clarity. What do you do with it? Well, you turn all that complex data into simple, powerful actions. All of this amazing science gets funneled into a tool called the Vanuatu Climate Futures Portal. It's basically a website that translates all the complex model outputs into these clear, easy-to-understand flood maps. Anyone, from a government minister to a village chief, can go online and see the specific risks to their own community. And the results are pretty stark. Just take a look at the projected impact on roads from a 100-year flood event. By 2030, you're looking at around 110 kilometers of road at risk. By 2050, that number climbs to 160 kilometers. And by 2090, it jumps to over 325 kilometers. This is the kind of concrete, specific data you can actually use to plan and prioritize where you're going to build stronger infrastructure. This project is, without a doubt, a monumental step forward, but it's also just a starting point. So what comes next? The team is really clear about the model's limitations. It's an incredible tool, but it's not a perfect crystal ball. The resolution can't capture every single tiny local wave effect, and right now, it doesn't model the double whammy of compound flooding, what happens when heavy rain and overflowing rivers combine with a storm surge. Knowing these limits is just as important as knowing what the model can do. But even with those caveats, there is absolutely no doubt about the impact. As the project's own report concludes, this work represents a truly significant step forward for Vanuatu's ability to understand and, more importantly, prepare for its climate future. So thanks to this incredible digital twin, Vanuatu now has a clearer view of its future climate risk than ever before in its history. The science has provided the map. It's answered the question of what could happen. The question that remains, really, for Vanuatu and for all of us, is how we're going to choose to act on that knowledge.